So the next section in the paper is the results. And what's important to remember with the results is that you're providing a biologically meaningful, factual report without interpretation. So you're reporting what you found from your study without interpretation, but you need to do so in a way that relates back to the context of the study and its biological or ecological relevance. And again, it's really good to remember how your results link directly to your questions and hypotheses. And I find it very useful here to differentiate between the key results. So these are the most novel findings that address your study aims. So the most interesting results, if you like, and they will also be the focus of the discussion. But then very often we will have many supporting results. These support the key results and help with the interpretation of findings, but they're maybe not very novel and they won't be the focus of the discussion. One example I like to give here, I do a lot of work on soil carbon dynamics. I measure soil respiration in response to different treatments, for example, and I really need to include data on soil temperature and soil water content, because we've known for over 50 years that soil moisture and soil water content and soil temperature influence CO2 coming from the soil, so soil respiration. And we've known that for a very long time. These results are probably not particularly interesting. What is really interesting are the CO2 results, but I have to be able to show, for example, that temperature and soil water content differ or don't differ among my treatments to be able to interpret the differences in CO2. So in this case, my key results will be the big changes in soil CO2, and soil temperature and soil water content will be supporting results that I use to interpret my data on CO2. Now, one of the big issues with the results section, especially among ecologists, is that we tend to get lost in statistics. So there is a very big focus on statistical testing and modeling and providing significant p-values. And it's really important, if we want to provide a biologically meaningful report, and we want the readers to be able to understand what our results mean, we need to remember that we're using statistics to support the ecology. So we use statistics to support statements in the results. We're not using statements to support statistics. So again, the ecology needs to be at the center of the results. And another thing to remember is again, you know, the hypotheses should give the magnitude and direction of effects we're expecting. So our results also need to give the magnitude and direction of effects. So instead of saying X and Y were significantly different, we might want to say X was 15% higher than Y. And then we give our statistics in parentheses after the results. So if we make very clear statements about the ecological meaning of treatments, patterns, and effects, we can help the reader understand our results. And also the reader will start thinking about the results and interpreting the results as they read. And obviously you would like them to come to the same conclusion as you do in the discussion. So using these clear statements, biological statements, about your findings, your results, is quite important. So I want to show you here two completely different, or they're actually the same results. Here I've written them without any statistics to make them clearer, and you can look at these on your own time at home. But essentially, the first text uses statistical terms, the second text uses real world terms, and I wanted to show you this as an example. Here we see, for example, the statistical terms. We have things like significantly positively correlated with, significantly negatively correlated with, marginally significantly correlated with. Now, this is not only hard to read, but it also means that the reader has to think for a moment, even if it's just a second. Significantly positively correlated, that means increases with. Okay, and it's that second when you have to do that with each sentence, you have to take a moment and go, yeah, that means an increase, that means a decrease, that means this increases and that declines. That is actually already a barrier to understanding. So instead, we use words like declined with, increased with, and here you can also see I've given an example, a non-significant trend towards lower foliar NP ratios, and that can help the reader create a picture of the results in their mind. What I've also done here is these are quite complex results in this case. I've actually started this section of the results with a summary statement that provides context. So here I've written, interestingly, foliar NP ratios were influenced by shifts in the concentrations of both N and P, depending on the global change driver. Now, what I've done there is I've summarized this section already, and I've signaled to the reader that actually this is going to get complicated. So I have changes in nitrogen, I have changes in phosphorus, and it depends on which global change driver is having an effect on foliar NP ratios. And that means that the reader is now prepared for me talking about changes in nitrogen, changes in phosphorus, and different global change drivers. So I've provided the reader with the context they need to understand that complexity. So again, I started big and I'm building in the detail and complexity. So you can try this at home to improve the readability of your results. So start each paragraph, for example, of the results using what we call a topical sentence that provides context. So this topical sentence basically tells the reader, this is what's coming. This is what I'm about to talk about. This is sort of like, this is the crucial information you need to know. Then, as you're writing your section, always remember to give the magnitude and direction of effects, use biological terms, and then build in the statistics and numbers. And what I like to do, because I'm just as guilty as everyone else of focusing too much on the statistics, what I like to do, and what I always tell my students to do, is to make figures. So always look at your data, always look at the figures first, even before you start analyzing, and then also write the first draft of your results by referring to those figures. So without the output of statistical texts, can you see your results in the figures? What do you see? And then write your results based on that, adding in the statistics and numbers later. And what's important here, and what I always tell my students, is if you have a statistically significant result that you can't see in your figures, you have a problem. So either your statistics are incorrect or your figure is not effective. It's usually the former. It's usually that your statistics might need revising, but it could also be that your figure does not show the result to the best effect. So This is one of the most important aspects of the results. Your figures should show each result at a glance. So the reader should be able to look at a graph like this one and see, oh, the number of publications declines with the amount of beer that is consumed. So in this case, we don't know that whether researchers drinking more beer produce fewer publications, or whether they drink more beer because they don't have many publications, but we do see in this case that there is a very clear correlation between the two. So figures should show your most important results at a glance, and tables are best used for things like summary data or site characteristics. Most people will find it much easier to interpret a figure than a table. And one tip here is that if you have a section that reads like a very long list of numbers, then you probably need a table instead. So tables are great for sort of overview of characteristics and summary data, and figures for the key results. And there's a nice paper in PLOS Computational Biology that outlines the 10 rules for effective figures. I've picked out the 7 most relevant ones to ecology here. The first is putting yourself in the reader's shoes. How can I show the reader what I need them to see? The second is then, obviously, you need to identify your message. What is important? What do I need to show? You need to provide very clear self-explanatory legends, and I'll come to that in a moment. Use colour and symbols effectively, for example, to highlight differences between treatments or sites. It's obviously very important not to mislead the reader. So you want the reader to see your results at a glance, but not manipulate the reader into seeing something that isn't there. Avoid clutter. So I've seen some really, really beautiful figures with lovely colours and lots and lots of detail, but I cannot see the result. And that means the figure is too cluttered. I need to be able to see that result, that difference between treatments or sites, or that relationship between variables. And that means that basically the message to the reader is more important than the beauty of the figure. So you can have the most beautiful figure, if the reader can't see that key result, can't get the message, then you've created an artwork and not an effective scientific graph. So one important aspect to remember when you're creating your figures and writing figure legends is that a lot of people will not read the results text. They will look at the figures and work out the results from the figures. So your figure legends must be understandable to somebody who hasn't read the paper, who hasn't read the text. They're just looking at the figure and the legend. And what I'm showing you here is quite a funny one. This is actually a real figure out of the European Urology Journal from 1993. We have a picture of a rat with a rather strange underpant, and all the legend says is the underpant worn by the rat. Now, at this point, everybody is thinking, why is the rat wearing an underpant? And is it important that it is a specific underpant? And all of these kind of things. So what on earth is this rat doing? What are the researchers doing to this rat? Loads and loads of questions. We have no idea. We cannot interpret this figure based on the information provided. So here's another example. This is a very simple box plot, where we can just take a moment to think, what do we need to know to understand this figure? So if I show you this figure, what information do I need to supply so that you can understand and interpret this figure without referring to the text? Now we can see across the top, I have abbreviations, L+, CT, and L-. I have methane flux on the side. I have two different colors. There are obviously the box plots. There are also some circles and the x-axis week of the year. And I've got these different top and bottom panels. So one of the important things is, where is this study? Where is the methane flux from? Where is this located? When was it carried out? So I've given week of the year, but actually, you know, unless I really, really think, I don't know what season this is. I don't know what month this is. All of this is quite important. Then I need to explain all abbreviations. I need to explain all of my symbols, and that includes what the box plots delineate. And then I need to give things like means, errors, and sample sizes. And then any other key information that the reader might need to be able to interpret this figure. So here is actually the legend to this figure. So we have soil methane fluxes. That's the first sentence. So now we know methane fluxes are coming from the soil. Under individuals of two common tree species, we have Hysteria cancina, red top panels, Simera aruba amara, blue bottom panels. So there we have our colours. In experimental litter removal, control and litter addition treatments, and there I give the abbreviations, in a tropical forest in Panama, Central America. So location of the experiment, measured weekly from March to July 2014. And then I've also put during the transition from the dry season to the wet season. Then right at the end, ranges, so boxes and whiskers and median lines are shown for n equals 4 individuals per species and treatment. What is missing here is that circles denote outliers. So if we go back to the graph, the only thing missing are these little circles, that they're outliers. But what I wanted to show you in this figure is that I mentioned the transition from the dry to the rainy season. And if you look at the graph, you can see that there's a very clear pattern in these methane fluxes. Everything is below the 0 line up to about week 20, and then above the 0 line from week 22 onwards. This is my transition from the dry to the rainy season that I describe here in the legend. So I'm using the legend to direct the reader's focus to this transition. And of course, in this case, we could have done it even better by shading, for example. So having two different shades, wet and dry season, that would have made it even more obvious. But the important thing here is that the legend explains everything I can see in the figure. I don't need to read the results section. And if you see what I've done here, I've started with a sentence that summarizes exactly what the figure is about. So soil methane fluxes under individuals of two common tree species. And then I've successively built in detail, ending with the things like sample sizes and what all the other symbols are. So in this case, what the boxes and whiskers are. So essentially, I've done the same funneling technique here in my legend as I've done in the rest of the text. I've started big, I provided a topical sentence, and then I've built in complexity and detail. So I've started big, finished small, even in the legend.